So it's going to be 30 divided by 44.094 times 3 times 44.01. So let's go ahead and plug that in. Let's get that answer. So you should get 89.83 grams of carbon dioxide. This right here is the theoretical yield of CO2. So this is the maximum amount of carbon dioxide that can be produced in this chemical reaction. If we only have 30 grams of propane, this is the greatest amount of CO2 that can be produced by burning 30 grams of propane. So now that we have the theoretical yield, let's go ahead and calculate the percent yield. As was mentioned before, the percent yield is going to be the actual yield of the product divided by the theoretical yield times 100%. So if we take 70 divided by 89.83, it will give us a percent yield of 77.9%. So this is the answer to the problem. And that's how we can calculate the percent yield of CO2 in this example. In this video, we're going to talk about how to calculate the theoretical yield and the percent yield. So here's a question that we start with. 45.2 grams of iron metal reacts with excess oxygen gas to produce 58.1 grams of iron oxide, Fe3O4. What is the theoretical yield of Fe3O4? Well, to begin, we need to write a balanced chemical equation. Iron metal is Fe, oxygen is O2, and this is going to produce Fe3O4. Now, there are 3 Fe atoms on the right side, so we need to put a 3 in front of Fe. There's 4 oxygen atoms on the right, so we need to put a 2 in front of O2. And now everything is balanced. Now, how can we find the theoretical yield of Fe3O4? What you need to know is that theoretical yield always applies to the product. It could be the moles of the product or the grams of the product. Once you find the theoretical yield, you can use it to calculate the percent yield. Now everything is in grams, so we're going to get the theoretical yield in grams as well. So we're going to find out what is the maximum amount of Fe3O4 that can be produced in this reaction. That is the theoretical yield. So what we need to do is to convert the grams of Fe, that's the limiting reactant. We need to convert that to the grams of Fe3O4. O2 is the excess reactant. So now, in order to convert the grams of one substance into the grams of another substance, it's a 3-step process. We're going to start with the grams of Fe, and we're going to convert it to the moles of Fe using the molar mass. In the second step, we're going to use the molar ratio to convert from moles of Fe to moles of Fe3O4. So basically, in the first step, we're changing the unit grams to moles. In the second step, we're changing the substance from Fe to Fe3O4. And in the last step, we're going to convert to grams of Fe3O4 using the molar mass again. So let's start with what we're given, which is 45.2 grams of Fe. Now the molar mass of Fe is 55.85 grams per mole. So the unit grams of Fe will cancel. And now let's change the substance from Fe to Fe3O4. So it's a 3-to-1 ratio. So for every 3 moles of iron metal that reacts, 1 mole of Fe3O4 will be produced. So now let's convert this back to grams. So we need to find the molar mass of Fe3O4. So there's 3 Fe atoms and 4 oxygen atoms. 1 mole of iron oxide has a mass of 231.55 grams. Always make sure that every other unit cancels, except for the unit that you want, which is grams of Fe3O4. So now let's perform the operation. It's going to be 45.2 divided by 55.85 divided by 3 times 231.55. So this is the theoretical yield, 62.5 grams. So that is the maximum amount of iron oxide that can be formed in this reaction. You can't get any more than this. So that's the answer to part A. That's the theoretical yield of Fe3O4. Now let's move on to our next step. How can we find the percent yield of this reaction? The percent yield is equal to the actual yield divided by the theoretical yield times 100%. So we have the theoretical yield. We know it's 62.5. But what is the actual yield? The actual yield is the grams or the mole.
Halo para pengejar. Kejar ini, kejar itu, kejar. Keep calm, gak ada kata telat. Pesan Grab Bike ada jaminan anti ngaret.
Moles of the product given to us in the reaction or in the problem. We were given that 58.1 grams of Fe3O4 was actually produced in this reaction. So that is the actual yield. The actual yield should be less than the theoretical yield. It should never be more. And it should correspond to the same substance, Fe3O4. So let's divide 58.1 by 62.5 and then multiply that result by 100. So the percent yield is 92.96, which we could say it's roughly about 93%. So that's the percent yield of this problem. So this particular situation is 93% efficient. Now let's move on to part C. Okay, I didn't want everything to be deleted. Now keep in mind the theoretical yield is still 62.5 grams. We're going to need that value. Part C, what would be the actual yield of Fe3O4 if this reaction was 75% efficient? If the process was 100% efficient, the actual yield will be the same as the theoretical yield. So the theoretical yield is 62.5. If it was 100% efficient, that's how much product we would get in the reaction. And this is supposed to be Fe3O4. I don't know why I keep writing it as Fe. So if it's 75% efficient, that means in the course of the reaction, we should get 75% of the theoretical yield. So all we gotta do is multiply 62.5 by 75%. The decimal equivalent of that is 0.75. So if it was 75% efficient, the actual yield will be 46.9 grams of iron oxide. Now granted, you can use the equation to get the answer as well. You could say percent yield is equal to the actual yield divided by the theoretical times 100. So the percent yield is 75%. You're looking for the actual yield. The theoretical yield is 62.5 times 100. So first you would have to divide both sides by 100. So 75% divided by 100 would give you 0.75. And then you would have to cross multiply. 1 times A is A, and that's equal to 0.75 times 62.5, which is 46.9. So all you need to do is just multiply the theoretical yield by the decimal equivalent of the percentage, and that's going to give you the actual yield. Go ahead and try this one. It's a similar problem to the last example. 50 grams of vanadium is mixed with 50 grams of ozone to produce 65 25 grams of vanadium 5 oxide. What is the theoretical yield of this reaction? So let's write a balance equation. Vanadium is V, ozone is O3, and we need to find the chemical formula of vanadium 5 oxide. So the Roman numeral 5 tells us the charge of vanadium. It's positive 5. Oxygen has a negative 2 charge as an ion. So this is going to be V2O5. So now we need to balance the equation. In order to balance the number of oxygen atoms, find the least common multiple between 3 and 5. 3 times 5 is 15. So we need 15 oxygen atoms on both sides. So let's put a 5 in front of O3 and a 3 in front of V2O5. Now we have 6 vanadium atoms on the left, so we need to put a 6 in front of V. Now this problem is a little bit different than the last one. In the last example, we were given the grams of just one reactant. We knew which reactant was limited and which one was excess. In this example, we don't know. So what I'm going to do is I'm going to convert the grams of each reactant to the grams of product, which is vanadium 5 oxide. The limited reactant will give us a lower theoretical yield. Whichever number is less, that's going to be the actual theoretical yield, and the reactant that gave us that answer is the limiting reactant. So let's start with 50 grams of vanadium. Let's convert it to moles. The molar mass of vanadium is 50.94 grams per mole. So 1 mole of vanadium is equivalent to 50.94 grams. Now we need to convert from moles of vanadium to moles of the product, vanadium 5 oxide. The molar ratio is 6 to 3. So for every 6 moles of vanadium that reacts, 3 moles of vanadium oxide will be produced. So we can cancel the unit grams of vanadium and moles of vanadium. Now we need to find the molar mass of vanadium 5 oxide. So there are 2 vanadium atoms in that compound and 5 oxygen atoms. So this is going to be 2 times 50.94 plus 5 times 16. 5 times 16 is 80, and 2 times 50.94, that's 101.88. So the molar mass is 181.88. So 1 mole of V2O5 has a mass of 181.88 grams. So now let's do the work. It's going to be 50 divided by 50.94 times 3 divided by 6, and then times 181.88. So we're going to get 89.26 grams of V2O5. Now you need to understand what this number means. It may or may not be the theoretical yield. We don't know. All we know is that if all of the 50 grams of vanadium reacts, if it's the limiting reactant, then 89.26 grams of V2O5 will be produced. We don't know if V is the limiting reactant yet, but we're about to find out soon. Now let's start with the other substance, 50 grams of ozone. And let's convert it to moles. The molar mass of O3 is 16 times 3, which is 48. So 1 mole of O3 has a mass of 48 grams. Now let's convert from O3 to V2O5. For every 3 moles of V2O5 that's produced, 5 moles of O3 will react. Now the last part's going to be the same. The molar mass of V2O5 is 181.88 grams. So as you can see, whenever you're doing a gram-to-gram conversion, the setup is still the So this is going to be 50 divided by 48 times 3 divided by 5 times 181.88. So if all 50 grams of ozone units, 113.675 grams of vanadium oxide will be produced. So therefore, looking at these two numbers, which one is the correct theoretical yield? The correct one is the lower number. It's this one. And the reactant that gave us that answer is the limiting reactant. So vanadium is the limiting reactant, ozone is the excess reactant. So the answer to part A is 89.26 grams. That is the theoretical yield. Now let's move on to the next part. What is the percent yield? The percent yield is equal to the actual yield divided by the theoretical yield times 100%. In our example, the actual yield is 65 grams of vanadium 5 oxide. That's how much was formed in this reaction. The theoretical yield, this is the most that we can produce in a reaction if we have a process that's 100% efficient. So the maximum vanadium oxide that we can produce is 89.26 grams. But we only got 65 in this experiment. So 65 divided by 89.26 times 100%. That means that this process was 72.8% efficient. So we only got 72.8% of how much we could have gotten in terms of the amount of vanadium oxide that was collected. Part C. How much vanadium oxide would be produced if this process was 90% efficient? So we're looking for the actual yield. The actual yield is basically going to be the theoretical yield times the percentage. So it's 89.26 times 90%, which is 0.90 as a decimal. So we just got to find out what 90% of 89.26 is. And it's 80.334. So if the process was 90% efficient, this is how many grams of vanadium oxide or vanadium 5 oxide that we would collect in this particular reaction. So hopefully this video gave you a good understanding of how to calculate the theoretical yield, percent yield, and even the actual yield if you're given the percent yield. So if a question says the process is 90% efficient, basically they're saying the percent yield is 90%. And what's the actual yield? So that's it for this problem. Thanks for watching, and have a good day. In this tutorial, we're going to go over gas stoichiometry problems. So let's start with this one. What is the volume of 2.5 moles of argon gas at STP? So what exactly is STP? STP stands for standard temperature and pressure. The standard temperature is 0 degrees Celsius, which corresponds to 273 Kelvin. The standard pressure is 1 atm. Now, what you need to know is that at STP, 1 mole of gas occupies a volume of 22.4 liters. And you can prove this using the ideal gas law equation, PV is equal to nRT. So let's plug in a pressure of 1. We're going to calculate the value of V. Let's replace N with 1 mole. R is the same, 0.08206. And the temperature is 273 Kelvin. So this will give you the volume, which is 0.08206 times 273. And so you're going to get a volume of 22.4 liters. So at STP, you can use this conversion factor. 1 mole of gas gas occupies 22.4 liters. Now, if 1 mole of gas occupies a volume of 22.4 liters, then what volume will 2.5 moles of gas occupy? So now we can set up a conversion factor. So 1 mole of argon will occupy 22.4 liters. So the unit moles will cancel. And so it's just going to be 2.5 times 22.4. So the answer to this problem is 56 liters. So for gases, you can use this conversion factor to convert moles to liters or liters to moles. So here's another problem. Let's say if you have 175 liters of oxygen gas. What volume, actually how many moles of oxygen gas are present at STP? Try that problem. So if you have 175 liters of oxygen gas at STP, how many moles of O2 are present? So start with what you're given, 175 liters, and then just convert it. There's 22.4 liters per mole of gas. So you just gotta divide by 22.4. And so 175 liters of gas corresponds to 7.81 moles of that gas. Now let's move on to our next question. Propane reacts with oxygen gas to produce carbon dioxide and water. What volume of CO2 will be produced if 8.4 liters of O2 reacts with excess propane gas? Well, first, let's write a balanced chemical reaction. So we have propane, C3H8, reacting with oxygen gas, and it's going to produce carbon dioxide plus water. Now, to balance this combustion reaction, the first thing we gotta make sure is that the number of carbon atoms are the same on both sides. So I'm going to put a 3 in front of CO2. So we have 3 carbon atoms on both sides. Now we have 8 hydrogen atoms on the left, which means I need to put a 4 in front of H2O. 4 times 2 is 8. Now I have 6 oxygen atoms from the 3 CO2 molecules. 3 times 2 is 6. And I have 4 oxygen atoms in the 4 water molecules. 4 times 1 is 4. So I have a total of 10 oxygen atoms on the right side. 10 divided by 2 is 5. So I need to put a 5 in front of O2. And so now I have a balanced chemical equation. So in this problem, I need to convert 8.4 liters of O2 into liters of CO2. Propane gas is the excess reactant, so I don't have to worry about that. Now for gases, you can do a liter to liter conversion the same way as you would do a mole to mole conversion. So we have 8.4 liters of O2. Now the molar ratio between O2 and CO2 is 5 to 1. So for every 5 moles of O2 that reacts, 3 moles of CO2 will be produced. And since moles are proportional to liters when dealing with gases, we could say that for every 5 liters of oxygen that reacts, 3 liters of CO2 will be produced. Keep in mind, 1 mole is equal to 22.4 liters, so moles and liters are proportional for gases. That's why you can do a liter to liter conversion and get the right answer. So all we gotta do in this problem is multiply 8.4 by 3 and then divide it by 5. So the answer is going to be 5.04 liters of carbon dioxide. And that's it. That's how you can do a liter to liter conversion. Number 3. 7.45 grams of solid magnesium carbonate is heated until it completely decomposes into carbon dioxide and magnesium oxide. which is a gas, magnesium carbonate is a solid, and then plus magnesium oxide. Oxide has a -2 charge like carbonate, so magnesium and oxygen will combine in a 1-to-1 ratio. So that's the chemical equation. It's already balanced. We don't need to do anything to it. So now, how can we find the answer? We're given the mass of magnesium carbonate. We need to calculate the volume of CO2 gas at STP. So keep in mind, at STP, 1 mole of gas occupies a volume of 22.4 liters. So all we need to do is find the moles of magnesium carbonate, convert it to the moles of CO2, and then convert that to liters. So first we need to calculate the molar mass of MgCO3. So in magnesium carbonate, we have 1 magnesium atom, a carbon atom, and 3 oxygen atoms. So the atomic mass of magnesium is 24.305. Carbon is 12.01. Oxygen is 16. So if you add it up, you should get a molar mass of 84.315. Make sure this is correct. Yeah. So that's it. And the units for this is grams per liter. So now what are we going to do with this information? So now we can start with what we're given, 7.45 grams of MgCO3. Now using a molar mass, we're going to convert it to moles. So 1 mole of magnesium carbonate has a mass of 84.315 grams. So now we can cancel the unit grams of magnesium carbonate. Now we gotta change the substance from this substance to that substance. And the molar ratio is 1-to-1. So for every mole of MgCO3 that reacts, 1 mole of CO2 will be produced. Now that we have moles of carbon dioxide, we can now calculate the volume using the molar volume. That is 1 mole of gas, CO2 is a gas, occupies a volume of 22.4 liters. And so now we can get the answer. So it's going to be 7.45 divided by 84.315 and then multiplied by 22.4. So you should get 1.98 liters of carbon dioxide gas. This is the answer. Number 4. Solid magnesium nitride reacts with excess liquid water to produce ammonia gas and solid magnesium hydroxide. If 4.7 liters of ammonia gas was collected at 300 Kelvin at a pressure of 1.6 atm, how many grams of magnesium nitride was consumed in the reaction? Well, let's begin by writing the balanced chemical equation. So what is the chemical formula of magnesium nitride? Magnesium, as was mentioned before, has a +2 charge. Nitrogen has a -3 charge. So to combine them, it's going to be Mg3N2. And it's in a solid state. Now it's going to react with liquid water, which is just H2O. And it's going to produce ammonia. Ammonia is an H strip. And it's in a gaseous state. And we're going to get magnesium hydroxide as a product. Hydroxide is OH minus. So to combine these two, we're going to get Mg1OH2. which we can simply write it as MgOH2. Now let's balance the chemical equation. So how can we do it? Notice that we have 2 nitrogen atoms on the left side. So we gotta put a 2 in front of N. Now we have 3 magnesium atoms on the left, which would imply that we need a 3 in front of MgOH2. So now notice that we have 6 oxygen atoms. So that implies we need a 6 in front of H2O. And we have a total of 12 hydrogen atoms now. 6 times 2 is 12 on the left. 2 times 3 is 6. 3 times 2 is 6. So that works out. So everything is balanced at this point. To solving this problem. We're told that water is the excess reagent, which means that magnesium nitride is the limiting reagent. So the amount of ammonia that's produced is directly tied to magnesium nitride. Now we're given the information for ammonia. We got the volume, the temperature, and the pressure, which means we can calculate the moles of NH3 produced. Which can help us to determine the grams of magnesium nitride that was consumed in the reaction. So first, let's use the ideal gas law. PV equals nRT, this equation, to calculate the moles of NH3 that was produced in the reaction. If we could find that, then we could use that to calculate the grams of magnesium nitride consumed. So the pressure is 1.6 atm. The volume of ammonia is 4.7 liters. Our goal is to calculate N. R is a constant, and the temperature is 300 Kelvin. So first, let's multiply 1.6 by 4.7. So that's 7.52. And then let's multiply 0.0826 times 300. So that's 24.618 times N. So to calculate N, we gotta divide 7.52 by 24.618. So that's gonna be 0.3055 moles of NH3. So now we need to convert moles of NH3 to grams of Mg3N2. So let's start with this value that we now have. So first, we need to use the molar ratio to change the substance from NH3 to Mg3N2. And we have a 1:2 ratio. So for every 2 moles of NH3 that are produced in reaction, 1 mole of magnesium nitride will be used up. So now we can convert it to the grams of Mg3N2. So let's find the molar mass. We have 3 magnesium atoms and 2 nitrogen atoms. So that's going to be 3 times 24.305 plus 2 times 14.01. And so that's about 100.935. So 1 mole of magnesium nitride has a mass of 100.935 grams. So it's going to be 0.3055 divided by 2 times 100.935. And so the final answer is 15.42 grams of magnesium nitride. So that's how many grams of that reactant that was consumed in this reaction in order to produce 4.7 liters of ammonia under these conditions. Number 5. 4.85 isolated and collected at 37 Celsius at a pressure of 1.52 atm. So how can we do this problem? Well, let's start with a balanced chemical reaction. So we have ammonia reacting with oxygen gas, and it's going to produce water plus nitrogen gas. So how can we balance this chemical equation? Well, we have 2 nitrogen atoms on the right side, so that may imply that we should put a 2 in front of NH3, which now means we have 6 hydrogen atoms on the left. So we should put a 3 in front of H2. And so now we have 3 oxygens. To get 3 on the left, 3 divided by 2 is 3 over 2. And so this is going to give us a fraction. Whenever you get a fraction like this, multiply everything by whatever number you see in the denominator, which is 2. So we're going to multiply everything by 2. So let's put a 4 in front of NH3. So now we need a 2 in front of N2. And 4 times 3 is 12. So we need 6 in front of H12. And now that we have 6 oxygen atoms, we need a 3 in front of O2 to have 6 on the left. And now the reaction is balanced. Now what should we do next? How can we calculate the volume of N2 produced? Whenever you wish to calculate the theoretical yield, or the amount of product that's produced, you need to identify the limiting reactant. And in this problem, we don't know which one is the limiting reactant as of yet. We have information for NH3 and O2. So in order to find the limiting reactant, we need to calculate the moles of every substance first and see which substance has the lowest mole per coefficient ratio. So I'm going to use PV equals nRT to calculate the moles. So to solve for n, divide both sides by RT. So PV divided by RT is equal to n. So the moles of NH3 is going to be the pressure, which is 1.45 atm, times the volume of 4.85, divided by R, which is 0.08206, and then we have a temperature of 27 degrees Celsius. So we need to convert that to Kelvin by adding 273 to 27, which is 300 Kelvin. So 1.45 times 4.85, and if you take that result divided by 0.08206, and then divide that result by 300, the moles of NH3 that you should get is 0.2857. Now let's do the same thing with O2. So the pressure is 1.63. The volume is 5.23. And then we have R. And then multiply by the temperature, which is 32. 32 plus 273, that's 305 Kelvin. And so the moles of O2 is 0.3406. So now, which one is going to be the limiting reactant? Is it O2 or NH3? To find out for sure, divide the moles by the coefficient, which we can see here, and see which number is lower. 0.2857 divided by 4 will give us a mole per coefficient ratio of 0.0714. And in the case of O2, 0.3406 divided by 3 is 0.1135. So NH3 has the lowest mole per coefficient ratio, which means it's the limiting reactant. It's going to calculate the volume of N2 produced. So first, let's calculate how many moles of N2 that will be produced. So we're going to start with 0.2857 moles of NH3. And the molar ratio is 4 to 2. So if 4 moles of NH3 reacts, 2 moles of N2 will be produced. So 0.2857 times 2 divided by 4. That's about 0.1429 moles if you round it. So now that we have the moles of N2, we can use that to calculate the volume of N2. So using the formula PV equals nRT. So the pressure of N2, we have it as 1.52 times V, which is what we're looking for, equals N, which is the moles is 0.1429 times R, 0.08206, and N2 is collected at a temperature of 37. So we got to convert that to Kelvin by adding 273. So 37 plus 273 is